Good evening, everyone. Today we have a pleasure to attend the talk by Professor Chris Godsil, who joined the CINDO department 37 years ago. And Professor Godsil is the best expert in the world in algebraic combinatorics. He started the Journal of Algebraic Combinatorics, and he authored two classical books on the subject, Algebraic Graph Theory and Algebraic Combinatorics. He has been a pioneer in using algebraic combinatoric techniques in quantum computing. And you might have also noticed that there are some events planned over this weekend to honor the 75th birthday of Professor Godsil. And the thing that I would like to mention why we have such events easily organized at CINDO, it's because Professor Godsil was an excellent supervisor for his graduate students. He won Excellence in Graduate Supervision Award at the university, and so we have quite an active group of students who keep coming to Waterloo and keep organizing such events. So thanks to Professor Godsil, and thanks for the students to make this event happen.
Thanks, Godsil. It's a pleasure to be here again. Of course, it's a long while, and I guess you'd forgotten what it used to be like, and you made a mistake of inviting me again. So I was going to talk about graph theory and quantum computing, and really it's a sense, a lot of it's how I got from this innocent questions to this mess. But we'll make that clear as I go on. So there'll be sort of some history involved, not just results. So in a sense, the problem started with questions about co-cliques in graphs, which are called independent sets or stable sets, but I'm going to be calling them co-cliques today. Well, see, what happened was when I first got here, Gordon Royal was here on a postdoc with Ron Reed, and we were working together. And eventually we started writing my book on algebraic graph theory. And there was a nice survey article by Hahn and Tardif on graph homomorphisms. And we thought, well, we're writing a book on algebraic graph theory. Biggs has already written a book with the same title, so we've got to put in some things that aren't in Biggs' book. And homomorphisms seemed interesting, and we had the survey there, so that made the writing quite easy. So we put in a couple of chapters on homomorphisms and co-cliques, and thought we were done with it. I mean, you write a book, you put things down, you can forget about it. It's all there. You don't need to think about it again. But Karen Ma didn't know that rule, so she wrote to us from Ottawa and asked the following question. So you're given a graph, you're taking the partitions of a set of size 9, must be 1 through 9, into three disjoint triples. Okay, and it's a combinatorial exercise to see that there's 280 of these things, but you can work on that. Now, so that tells you what the vertices of the graph are going to be, these partitions. What's the adjacency rule? Well, the adjacency rule is that they're crossed. So each triple in one partition meets 3 of the triples in the other, all 3 of the triples in the other. So it's an adjacency rule. Now, in fact, the number of ways, the number of cells in the meet of 2 partitions, there's about 5 or 6 different values. I don't care at this point, but anyway, so in this case, you'd have 9 cells in the intersection, okay? And so that was the graph that I was concerned about. And the question she asked is this graph a core? Now, of course, I need to explain what a core is, but a couple of things. The first thing is that there was claimed that this was based on some problem in testing computer chips. I suspect it was good enough as a description for grant application purposes. I'm not entirely convinced that it was actually a really practical problem, but it was coming from that problem. And so the idea was, well, I'll explain what a core is in a minute. In a sense, if the graph wasn't a core, they could speed up what they were doing. So what's a core? Well, we have to define in terms of homomorphisms. So homomorphism is just a map from the vertices of one graph to another that takes adjacent vertices to adjacent vertices. Now, the only thing to bear in mind is that 2 vertices, a vertex is not adjacent to itself, not for me, not today, okay? So I can't map 2 adjacent vertices to a single vertex. In fact, the pre-image of each vertex would be a co-clique. Okay, this is the rule. Now, there are an important class of examples. I mean, isomorphisms of graphs are homomorphisms, and colorings are homomorphisms. And so, in a sense, you can say that if you're working on coloring problems and you decide they're too easy, you can go and work on homomorphism problems, covers an even larger range of problems. So, a graph is a homomorphism, sorry, a graph is a core if any homomorphism of the graph to itself is actually an automorphism. So you don't have to worry about these newfangled homomorphisms, everything's just an automorphism. And so the question is whether this graph on 280 vertices was a core. If it wasn't, then as I said, this would in some sense lead to speed up to an algorithm. And so, well, that was a, so there's the definition of a core. Now, the problem is how do you show a graph as a core? It's not, there are various tricks you can use, and the canonical example we had in mind was the Kneser graph, which I'm calling KV colon K. So this is the graph, the vertices are the K subset of a set of V elements, and two K subsets are adjacent if they're disjoint. Now this is a nice graph. If you take V colon 1, you're just getting the complete graph, and K52 is better known as the Peterson graph. So there are some graphs there. There are interesting families of graphs. The Erdős-Rada theorem tells you that the maximum size of a coclique in the Kneser graph is V minus 1 choose K minus 1. And you can get such a coclique by taking the K sets which contain a given point from 1 through V. So that bounds tight. And in fact, you can prove that any set of any coclique of this size has exactly that form. So from my point of view, there are two parts to the Erdős-Rada theorem. One is that there's a bound on the size of cocliques, and the second is that you have a characterization of the cocliques that meet the bound. And I would actually argue that the second part is more useful. Okay, there are a number of ways of proving this, and some using eigenvalue bounds, for example, and various tricks. But we can prove it. The reason this comes to mind is because we knew that this graph was a core, and the proof of this graph used the characterization of the cocliques of maximum size. So with that in mind, we go back to our partition graph, which is, partitions of sets, not subsets of sets, but it seems close enough. And so then we start thinking, well, can we do something similar there? Okay. Actually, do I want to say? So we could, actually I say we, a lot of this was done by Mike Newman. He was working on his PhD with me at the time. We came up with a proof that this guy was a core. Now, what happened is about this time the Perimeter Institute was in place, and the physicists were swanning into the Perimeter Institute, and occasionally they would come up to Mike Mosker or somebody and say, they've got this problem in graph theory. And then Mike, next thing I know, this physicist is blocking my office door with this question. And so we had some idea that there was some, the stuff that Gordon and I were doing was of interest to physicists, because he was collecting citations of our book for the Brownie Point collection at the end of the year once, and he noticed that we were being cited by papers in physics. That was interesting, but we left it at that. But now the physicists were coming in, and they had quite a concrete question. You're taking the graph, another graph now, whose vertices are the plus or minus 1 vectors of length d. So there are 2 to the d vertices, okay? And 2 of them are adjacent if they're orthogonal. And the question is simply, what is the chromatic number of this graph? I said, yeah, what's the chromatic number? Now, there are some special cases. If d is odd, then the graph is empty. There are no edges, so I can do that. If d is even, well, this could be, after you've got the 280 vertices for the partition graph, you can then check that if d is congruent to 2 mod 4, then the graph is bipartite, great number 2, so that's a problem. So the only gets complicated when d is equal to 4 times, or d is divisible by 4. And the conclusion, and it depends on the deep paper due to Frankel and Rödel, is that the chromatic number of this graph, if d is divisible by 4, increases exponentially with d. Okay, so we knew that. Okay, but that wasn't what was bothering the physicists, because the physicists had come up with this concept of a quantum colouring. And they knew that, that this graph had a quantum decolouring. which is a lot smaller, less exponential bound. And so they therefore knew that if D was large enough, they would have examples of graphs which had a quantum decoloring, but did not have a classical decoloring. The classical decoloring would require an exponential number of colours. And so they wanted to know when these two things were different. Now, Frankel and Rödel, you can dig through a result and you probably got some doubly exponential number of vertices or something, so it wasn't a question in that sense. But the question was, what's the first case where it goes wrong? Okay, and so, well, let me see what I'm going to say next. Well, there's a few things we can do to help us. A clique of maximal size in this orthogonality graph is just an orthogonal basis for R to the D. In fact, if you write down the matrices as columns, you get an n by n matrix with entries plus or minus 1, call it H, then H transpose H is n times the identity. It's a Hadamard matrix. So you can show that the maximal cliques in this graph are the Hadamard matrices. Now, it's not unusual for problems in sort of algebraic graph theory where you're trying to characterise maximal cliques and you suddenly discover they correspond to some structure which is apparently unrelated. So the maximal cliques in that partition graph correspond to affine planes. So there's often some geometry hiding there, okay? But the maximal cliques correspond to the Hadamard matrices. And now, if a Hadamard matrix exists, it's easy to prove that 4 divides the order. And here's a concrete example of a Hadamard matrix of order 2 to the m by 2 to the m, which you can do for any m. And particularly, if the Hadamard matrix exists, then the chromatic number of omega d is at least d, because that's the clique number. Now, the problem is that well, there's lots of Hadamard matrices around, but the largest integer d for which it's unknown whether there's a Hadamard graph is below 1,000. I've forgotten what it exactly is. So that's actually it's one of the longest, most hardest questions in algebraic graph theory. Is it true that if 4 divides n, there's an n by n Hadamard matrix? And that's been open for many, many years. Okay, so we have the Hadamard matrices giving us the cliques. Now, it's also clear that the chromatic number of the graph is lower bounded by number of vertices divided by the maximum size of the co-clique. Okay, and so that suggests maybe we could look at what this is. And now our co-cliques are coming back again. And well, there's a nice result which history is a little complicated. It goes back to Delsart and then Hoffman. If you have a k-regular graph on n vertices and the least eigenvalue of the graph is tau, now the eigenvalues of the graph sum to 0 because that's the trace of the adjacency matrix, okay? And so tau is negative, just to make it easier. And then it says that alpha, the size largest co-clique, is bounded by that. I guess a third exercise is you can verify this is tight. Well, no, it doesn't. It's certainly tight in many cases. It's tight for the complete graphs. But it gives us this bound. So that the maximum size of a co-clique is 2 to the d on d. Okay. Now, and so in particular, if d does not divide 2 to the d, then the chromatic number of the graph is greater than d. Okay, so in a sense, the only cases we have to worry about now are the cases where d is a power of 2. Okay, and so we're worried about the maximum size of co-cliques, and well, Mike was doing this for his living at that time, and so he proved this, that if d is a power of 2, then the chromatic number of omega d is d if n is less than or equal to 8 and is greater than d otherwise. So the first case at which the quantum chromatic number and the classical chromatic number differ is at 16. Okay. For 8 depended on a computer computation by Gordon Royal. But again, he was working with co-cliques, and so the fact that this was of interest to the physicists, well, that's why we did it, but we weren't looking for work in physics. And so we got a complete solution. It was proved, the physicists had actually realized that 16 was the first case to look at about the same time. So that was one source of problems on where our algebraic graph theory was leading us into quantum problems. The other problem is, well, this is the early days of quantum computing, and they were asking questions about computing automorphism groups of graphs. And you can phrase the question saying, is there a quantum algorithm for graph isomorphism? that is faster than any classical algorithm. Now, the reason for picking on the graph isomorphism is because it's not known to be, it's almost certainly not NP complete, and probably not polynomial, so it's got an interesting complexity situation. And so the physicists felt that there might be a reasonable chance of getting a faster algorithm. No physicist ever suggested they would get a fast algorithm for an NP complete problem. Okay, but so they thought there might be some chance of doing a faster algorithm. Now, I also have a quote from a friend in quantum computing told me once that a quantum computer in the future will have just two buttons, one labelled Shaw and the other labelled Grover. And the point here is that there's not a long, there's only a short list of things you can do on a quantum computer that you can't, where it's usefully faster than a classical computer. Okay, and so there's an incentive for, if you could find a nice algorithm for graph isomorphism, that would be really quite impressive. And so some of these physicists dropping in the Premier Institute would be getting in touch with me, and the point is it's not too hard to dream up an algorithm for graph isomorphism, which on the face of it might have the potential of being faster than usual. Now, the usual algorithm these days is you stuff on a computer and you run Bren McKay's Naughty or something equivalent, and that works very well for graphs on tens of thousands of vertices. And so, I mean, it's faster than linear algebra, okay? So if you're doing computation, it's faster to use Naughty and then do the linear algebra than the other direction. So, but still, these don't run in polynomial time. So Terry Rudolph was a physicist who was visiting Premier Institute, and he'd come up with a construction of a graph. And so now I'm describing it. So it's called, I call it symmetric power because it is related to the symmetric power of matrices. They're sometimes called token graphs these days. So you've got a graph X on n vertices. The k-symmetric power of the vertices are the k subsets of the vertices of X, so there's n choose k vertices. And two k sets are adjacent if their symmetric difference is an edge, if you underline graph. Okay, so it's a bit hard to visualize, but that's a definition. That's not complicated. So the idea is that you would take the k-symmetric power of X, you would take it gives you a adjacency matrix. I'm just going to call that M of X, because the underlying principle for this, for the physicist approach to graph isomorphism, is you have a procedure which, given the graph X, produces a matrix M of X, and then you compute the characteristic polynomial of M of X and say that determines the isomorphism class. No, but you'd like it to. Okay, so in this case, M of X is the adjacency matrix of some symmetric power. Now, I was lucky because I was just asked about the symmetric square. So what happens, the physicists have these questions, they try and test it. They test it on a bunch of examples, okay? Some of them are more careful than others, but anyway, so you do some testing. Now, it turned out that for strongly regular graphs, I proved that, that if with strongly regular graphs, that this procedure fails, and fails easily. So strongly regular graphs have got parameters, and if you take two strongly regular graphs, same parameters, then the procedure will fail. And so you can construct strongly regular graphs from Latin squares. So if you have an n by n Latin square, the vertices of your graph are just the n squared positions, and two positions are going to be adjacent if they're in the same row, the same column, or have the same content. And so if you have an n by n Latin square, you get a regular graph on 3n minus 3 vertices. And any two of those graphs will beat this algorithm. Okay, so, and then, well, you could then ask, I mean, it's clear that you could then ask what if you use larger values of k, but then the problem is if you start using the larger values of k subsets, you're going to have a very big graph. Okay, and you want this to run in polynomial time, and so you don't want to have to take exponential time to construct the graph. But two groups of people independently took care of the larger case. So that was that one out, so we did that. So the second try was another group of people wrapped around Simone Severini. And so this was a construction which was motivated in some sense by what are called discrete quantum walks, which I won't be saying much about. So the assumption is so again, the problem is we're going to have our graph X, we're going to construct M of X, and then claim that the spectrum of M of X determines the isomorphism class. Okay. So if I take a graph, I'm going to define two operators on the space of functions on the nk arcs of x. So these are nk by nk matrices, but I find it a little easier to think of them as operators. So my graphs on n vertices has got, if it's regular, so it's got n vertices, so I'm going to be dealing with an nk by nk matrix, so it's not small, but it's still manageable. So I've got to define two operators on this space of functions. And one is just if you've got a function f, then the value of the function r of f is just the value of f on vu. So that's just, it corresponds just reversing an arc. And the second one looks a little more complicated, and there's a chance I've got a typo there, but that's close enough to indicate the principle. Is it right? Yeah, thanks. So we have these two operators. Now, the thing to notice here is that both R and C are involutions. R squared is equal to C squared. And what you'll work with for your discrete quantum walk would be this matrix, R times C, which is orthogonal or unitary. And so you get a discrete quantum walk by looking at powers of a unitary matrix. And so this is a valid choice. And so Grover's algorithm can be encoded in this form. So it's a standard way of doing discrete quantum walks, okay? And so we've constructed these two things. Now, so the conjecture was that if x and y are strongly regular and the two magic matrices are similar, then the graphs are isomorphic. Now, there's a couple of problems with this. The first is that they realised, I think, between the first edition of the paper and the second edition of the paper, that it was actually false for some fairly small regular graphs. In fact, there were counterexamples on 14 vertices. So then they refined the conjecture, and they put in the word strongly regular. Okay, so that narrows things down quite a bit. I've got my latent square graphs. Okay, and so they tested on the strongly regular graphs up to 40 vertices, which is a non-trivial thing. I don't know whether they tested the graphs and their complements. They may not have realised that the list on the web page only gives one of each class. But anyway, so they made this conjecture. Okay. Now, Crystal Go and I worked on this for a long while. I don't know why it was so annoying. And we had some counterexamples to that weren't strongly regular, and we'd had some theories about what we should be doing. And so we decided we needed, some fairly fancy graphs. These are again strongly regular. In fact, these strongly graphs have the property that not only is the graph strongly regular, but the neighbourhood of each vertex is strongly regular, and the things at distance 2 are also strongly regular. So they're very special graphs. And I'm just going to call them unitary generalised quadrangles, and I'll be kind and not tell you what that means. Okay. Now, the parameters I need are 25, 5. So it's finite geometry, so you have to add 1 to everything. So that means there's 26 points on each line and 6 lines on each point. So you've got an instant structure of points and lines. Okay, but let's not worry about that. And you get a strongly regular graph on 756 vertices. In fact, there are 2 of them. And they're quite closely related. There's a fairly simple construction, takes one to the other. And the conjecture was, the magic matrix they were using, they're going to take U cubed. U is that product R times C. What's the S plus? Well, the idea is you look at the matrix and set all the negative entries equal to 0. Now, that's a fairly brutal operation on a matrix. Okay, so you set all the negative entries to 0. So now you have a matrix. Now, for our particular example, we had a matrix of order 96,280 by 96,280. We actually had 2 of the suckers. And, we couldn't, obviously, we just work in Sage. Sage is not going to dream of touching Sage. So Crystal Go and I were moaning about this in the coffee lounge one day, and Tor Miklopust was there. And he started, he got interested and we explained what was going on. He said, I think I can do that. And I think he did it over a weekend. He did a computation and proved, as a probabilistic proof, but proved that that those 2 graphs get the 2 M's were cospectral, but the graphs weren't isomorphic. Okay, so that was a nice collaboration. So we, but it also indicates that, that was the smallest pair of examples that we could come up with. Now, So actually what happened with that is I said to Crystal, I think maybe we should go over to the dark side and start proposing algorithms for graph isomorphism and let the physicists prove that they don't work. Jamie Smith, another graduate student of mine, actually he disposed of another algorithm in the course of his PhD thesis. So it was fairly easy to dream up these algorithms. It's not always easy to prove they don't work. This particular one I just gave you was an extreme case. But so anyway, so these were problems in some sense. I was interested in automorphism groups and things like this, and so these are things I'd been thinking about. But then I started working on quantum walks, and that's a larger area, so I need to explain that. Excuse me, I'm going to have a sip of coffee. Now, I guess it was Simone Severini, which he was a postdoc at Perimeter, and he dumped this on us at some point, and they'd done some work. So for a continuous quantum walk, the word walk is missing. You start with a graph with adjacency matrix A, okay? And you have an initial probability density, and then you run the walk for a certain time, real number t, and then you do a measurement. Okay, now the idea is you say you've got an initial state and the state at time t. Now, life will be, classically when you do a random walk, you have the initial state would be a probability density on the vertices, so non-negative numbers on the vertices, something to 1. Okay, and so when you stop, you get something like this. But we're working with quantum physicists, so they're not going to do anything that simple. They're going to use density matrices in place of those matrices. A density matrix is a positive semi-definite matrix with trace equal to 1. Okay, and so, because of the axioms of quantum physics, and there is a quote that the axioms of quantum physics are not as strict as those of mathematics, according to the physicists, whatever that means. I collect these quotes. My favourite one recently I saw was that mathematically the points of complex projective space are all equal. So that takes care of all the problems in complex projective space because there's only one point. Yeah, but anyway, let's not go there. So we use densities for good reason. So it's a quasi-semi-definite matrix with trace 0. Because it's quasi-semi-definite, the diagonal terms are non-negative. And because the trace is 1, they sum to the identity, so that is a probability density. So you can view a density matrix as a generalization of a probability density. For the purpose of this discussion, I hope I'm not probably the ash from the people in the back. So we're going to start with a density matrix, and it'll have simple form, and things will run. And how it runs is going to depend on our graph, and then we'll get another density matrix. And we're asking questions about, if we start on this, can we get to this? Okay. Now, the other point I might notice is that physicists, I've never heard a physicist refer to these things as quantum random walks. Okay, because in some sense there's no randomness in the walk, the only randomness is in the measurement. So if the density matrix is diagonal, then you're back doing classical physics. And for purposes of this lecture, I'm just going to use diagonal matrices with one entry equal to 0 and the others equal to 1 and the others entries equal to 0. And because I'm a poor mathematician, I'm not going to use any brass and kets, okay, which would normally be used at this point. So this is just a diagonal matrix with a 1 in the A position and 0 else. And so that would be that's certainly a valid density matrix. Now, the issue is even if I start with that as my first density matrix, once I start running this walk, it's going to get messed up. And so I'm going to get some real density matrices, not just diagonal things. So how do you change it? How does it change? Well, you get change in quantum physics either by measurements, which we're not going to be talking about, or by unitary operators. So I've got a unitary operator, and it's going to hit the state D. It's going to be a function of time. So when I stop at a certain time, it's in a certain state, and then I can carry out a measurement, and I get certain observations, which I don't care about right now. So the rule is that if you start in this state, density matrix D, then your state at time t is given by that formula there. Now notice that this u of t is going to be a unitary operator, so this says that the state at time t is similar to the state at time 0. And so that tells me that this matrix is positive semi-definite and its trace is 1. So it's a mapping density matrices to density matrices, and that's what we care about. Now, well, the question is, what about this U guy? Now, before, when I was talking about discrete walks, I constructed it as a product of two involutions, but now we're doing something quite different. I'm just going to define it to be the exponential of I times t times an adjacency matrix. Now, if I was a physicist, I'd have a minus sign in there, but it's not going to affect anything I do, so I leave it off. I don't quite know how I got in that habit. Now, the point is, this is a unitary matrix, and it's also symmetric, which you don't normally expect for a unitary matrix. And that plays a role in some things, which I probably won't be talking about today. Now, okay, so, well, I can work with A. I mean, it's a matrix. I can compute eigenvalues and eigenvectors. That's all well and good. But I'm not working with A. I'm working with this U of t. Well, the trick is you can use the spectral decomposition. We can write A as a linear combination of eigenvalues times projections onto the eigenspace. This is the sort of the upmarket version of the fact you can diagonalize symmetric matrices. That's the useful form, really. Okay, this is what you actually use, not what they showed the kiddies in their undergraduate linear algebra. So we have that. Now, the nice thing about this, if you take any function of A, f of A, you just replace theta by f of theta, and you've now got the spectral decomposition for f of A. Now, there might be a few weirder words to be thrown around in some cases, but so you want f to be defined on the eigenvalues. Now, for U of t, it's x by t, so we're going to get this sum. So we're going to have the same idempotence, the same projections. The eigenvalue of theta r, which was real, now becomes this, e to the I t theta r, which is a complex number. And that's pretty good because you know that the unitary matrices, the eigenvalues are complex, so you get in trouble with anything else. So there we are. We have that. Now the point now is that you can work with this. You can prove things using this formula. You can actually do computations. Even in Sage, I can compute U of t without any particular problem. We do it regularly to, we're trying to test conjectures or get some idea what's happening. So we can construct this guy. You can find the idempotence, throw things all together. So that's not a problem. And now, remember I said my initial state D got mapped to this. Well, now I use my spectral decomposition, and it's a bit of a mess. I get two parts. I get, well, e to the IT eigenvalue difference times this product. Okay, and so, but anyway, so that's the formula. We'll see, we'll get a bit more out of that in a moment. Now, the question that the physicists, one of the first questions the physicists asked, and I'll explain why it's interesting in a moment, is, okay, given vertices A and B in graph, is there a time t such that if you start at dA, the time t, you're on dB. Now, dB is just plain old diagonal with a 1 in the B position. Now, if that happens, the jargon is you have perfect state transfer. And one reason this is interesting is because it means, in a certain sense, you can form a copy of if you've got a qubit in your quantum computer, you can construct another qubit which is in a copy of the state of that. So you can clone qubits in some sense. Now, there's a theorem in quantum physics that says you can't clone a quantum state. It basically gives the map that takes m to m tensor m is not linear, and operations in quantum must be linear. So, so this is potentially useful in a quantum computer. Now, we don't have quantum computers yet, and I'm not sure. But anyway, so they had valid reasons for wanting to look at it. So now, I mean, you can also start varying the states and ask other transformation, and I'm using the adjacency matrix. You can use the Laplacian or the sinus Laplacian. There are a lot of variants, but I'm sticking to the simple because if you want the more complicated version, you can see what I'm teaching in the graduate course of fields. So if I do get what I just showed you, I say I have perfect state transfer from A to B when A and B are different. If B is equal to A, then you say you have periodicity, and that does happen. And this is what this example shows. So one thing that's nice about this subject is the first useful example is only 2 by 2. And I can do the calculations there. So we start with the complete graph on two vertices of our graph. So there's the adjacency matrix, I worked it out. And just notice that the even powers of the adjacency matrix to the identity and the odd powers of the A again. Okay. And so U of t, this is a version of de Moivre's law for like e to the I theta is cos theta plus I sine theta. Well, you get, for matrices, you have much the same thing. You get U of t is cosine t times I plus I sine t times A. And I'm just going to observe here, if I take t to be pi, and if you remember your trig formulas properly, you get that U of pi is minus I. And so when you compute this, you get minus I d minus I, so you're back to where you started. So if you're looking at quantum walk on the two vertex graph, okay, and you start on one state, then at time pi, you're back where you started. So you've got a very expensive piece of hardware that you've got all sorts of grant money for, and it does nothing. Well, but we can do better. So the next one to look at is just pi on 2. And again, I worked it out there. And there's the formula. And if you trust my calculations, if you knew better, you wouldn't. Then you've transferred from this state, you can think of E1 transpose, to E2 transpose. So in this case, you've got transfer from one vertex to the other. You've got perfect state transfer. Okay. Now it turns out for the stuff we're dealing with that perfect state transfer and periodicity go hand in hand. If you get perfect state transfer at time t, you'll get periodicity at time 2t. And this is useful because if you're trying to find whether a graph admits perfect state transfer, it's often easier to first check whether it's got periodic vertices. But we'll leave it at that. So we have perfect state transfer. And well, what goes on at time pi and 4 is interesting too, but not that interesting that we'll go on today. So where does it give us? We get more from this than you might think at first. So for a graph theorist, a natural product is the Cartesian product. Copies of x vertically, copies of y horizontally. It's a Cartesian product. Okay, and so if you got tired of playing with x and y individually, you can look at the quantum walk on the Cartesian product. Turns out that the transition matrix of that is just the Kronecker product of the transition matrices of the two factors. And this is something that physicists love because this means you're now working with a composite system. Alice and Bob come out to play. Okay, so the point is that there's a graph theory side, graph theory side and a physics side, and it's a useful connection. In particular, if you take the Cartesian product of d copies of K2, you can show very quickly that you get perfect state transfer from any vertex to the unique vertex at maximum distance. And there's a unique vertex because the Cartesian product of d copies of K2 is the d cube. So now you've got perfect state transfer on the d cube without doing any extra work, really. Okay. And so, that's nice. So K2 works. The path on 3 vertices also works, but not everything works, and that's what I'll be finishing off with. Yeah, we're doing fine. So a natural question to ask at some point when you start playing with these things, okay, well, which pairs of vertices, U and V, have what properties must they have if I'm going to get PST from U to V? What properties must they share? Must they have the same valency? There's all sorts of questions you can ask, okay? Now, I can answer the valency question. The key thing to notice is, well, despite appearances, U of T, well, in the spectral decomposition, I had those projections E sub R. Each of those projections is a polynomial in the adjacency matrix, okay? And so U of T is actually a polynomial in adjacency matrix, so I don't need to know anything about exponentials, okay? And so that says in particular that U of T and any power of the adjacency matrix commute, which is just a polynomial, eh? And so if we have our equation here with transfer from A to B, then I multiply on the left by A to the K and on the right by A to the L, and I get this being transferred to this. Now, what I'm going to do is just take the trace of both sides, and that kills the U of T. Okay, and you can rearrange it a little bit, so and you get this. Now, this is just the number of walks, number of walks in the graph that have length k plus L and start and finish at A. The number of closed walks of length k plus L. And over here, you've got the number of closed walks starting at B of length k plus L. And those two numbers are equal. And so if you put k equals L equals 2, you get the A and B have the same valency, for example. Now you get quite a bit more because this is not just for one power of A, it's for all powers of A. And as a combinatorialist, if you're dealing with a sequence like that, you might want to use generating functions, though I won't show you that. Well, this is what we proved. One consequence of this is that if we get perfect state transfer from A to B, then this argument tells you that the graph you get from X by deleting A, X drop A, is co-spectral to the graph you get by deleting B, which is much stronger than just saying it's equivalent to the statement about walks actually, but it sounds better, perhaps. Okay, so there's a strong connection between the two properties. Okay, there's a rough interpretation that if you have a graph and you make a model of the graph where you use, say, some sort of ball for the vertices and join them by rods, hard metal rods, and you drop it, and you made it properly so it doesn't break apart, you'll hear a noise, and that noise will be a sum of different frequencies. And those frequencies, if you throw enough lies at it, will essentially be the eigenvalues of the graph. So the vibration modes of the graph are determined by the eigenvalues. Well, what if you're just a bit more careful? You pick up your model and have it hanging from a string or something and just tap one vertex. You will hear, again, a bunch of eigenvalues, but you won't necessarily hear all the eigenvalues in the graph. You just hear some of them, okay? And so in that case, and so what they're saying, if you tap at those two vertices, you hear the same things. And so it just depends on this sort of local spectrum. That will matter a little bit in a moment, okay? So, there is something we can say. Now, so that's telling us that we're asking these questions about perfect state transfer and things, and we're getting interactions with interesting linear algebra and combinatorics, okay? But there's more. Perfect state transfer also imposes a constraint on the eigenvalues. And so I'm assuming now that, so this is my standard setup. I'm starting with the state d sub A and I'm transferring d sub B. And the thing I want to point out here is most of the this is a real matrix. This is real. The projections are real. You're dealing with a symmetric matrix. So the only things that aren't obvious real are this. Now you can argue that, that these matrices are linearly independent because they're trace orthogonal, or various arguments. And so the conclusion then is, if this is real and these are all real, then this has to be real. Now it's e to the it, difference of eigenvalues. Now the eigenvalues of the graph aren't particularly nice. You can say they're algebraic integers, but they're not going to be, they're not integers. They're in general, they're a mess, especially if you pick a large graph. So this is can be a fairly horrible number. So you conclude that if this is real, it must be plus or minus 1. It's a complex number. And since I don't like signs and I get wrong with them, I'll take 2t and then it's equal to 1. Okay? So I get two equations from this. So I'm assuming that these matrices are non-zero, and that's related to my tapping vertices before, but I'm not going to go into that in any detail. But I get two equations from this, namely that t, theta r minus theta s, is some integer multiple of pi, and t of theta k minus l is another integer multiple of pi, which doesn't look very useful, but you can take the ratio of those two things. And you conclude that this ratio is rational. Now this is a surprise because, as I said, the eigenvalues of the graph are algebraic integers and not particularly nice. And so you've got an algebraic integer divided by an algebraic integer that will not in general be rational. Okay. Now there's some weasel words in this because I need to, I can only work with eigenvalues for which this projection is not zero, but that's not a problem. We can ignore that. Okay, so this is a number theory condition. So the physicists, when they looked at this, so initial papers on continuous quantum walks, they observed that, well, for a path on two vertices, you've got perfect state transfer, and you also get perfect state transfer of the path on three vertices, but you don't get perfect state transfer for any larger paths, and we have enough information to dispose of the path on four vertices now. We can work out the eigenvalues of the path on vertices because you can work out the characteristic polynomial. This is your fourth exercise. And it's t to the fourth minus 3t squared plus 1, which you can write in that form, and so it factors, and so you can get the zeros of this. It's product of quadratics. So let's do that. So I get 4 eigenvalues, as I should. Okay, and it's sort of Fibonacci number type things. Plus or minus 1 plus or minus root 5 over 2. And then I compute theta 1 minus theta 3 over theta 1 minus theta 2, and I get root 5 over 1, which is not in Q. So there is no perfect state transfer between the n vertices on the path on 4 vertices. So we're using number theory to prevent it. Now, more is true. You can actually show that if you do have PSD between the vertices and you look at the eigenvalues involved locally, they must be at worst lie in a quadratic extension of the rationals. So the integers are a quadratic extension of the rationals. And one thing I proved using this is that there are only finitely many connected graphs with maximum valency D. So you pick maximum valency D. There's only finitely many connected graphs with that maximum valency where perfect state transfer occurs. And so perfect state transfer is rare. In fact, a while back, I actually extended this. I can even extend this to infinite graphs with bounded valency if they're connected. You can't get perfect state transfer. And the physicists have drawn actually drawn down some infinite graphs and talked about perfect state transfer on those graphs, so it's not just me being silly. And so that's the end of the talk. Thanks for your attention. And I didn't have my usual end of talk slide, so Xiaohong gave me this.
Thanks for the great talk. So now it's question and answer period time. So if you have questions, please wait for me to pass your mic. We need it for recording to capture your question. Questions? Okay, everyone is shy. I will start. It's probably a silly question. You have this line of algorithm which you conjecture, I don't know, you conjecture that tests the graph isomorphism, but it looks like there were some counterexamples for them. But are there some classes of classes of graphs for which this algorithm really do test isomorphism?
Well, it's a fair question. I mean, it's more complicated than that, because the first one I was dealing with the symmetric powers. I mean, as it stands, it's not clear that even if you could prove that it's distinguished, it's not clear it's useful. You've got to implement it. And so Terry Rudolph's idea was, well, this is quantum mechanics. Maybe there's a way we can speed up that calculation. So there's a lot more going on in this than just the isomorphism question. You've got to actually be able to implement it. Okay, and so it's not just a physicist, of course. There's over the years, there's many papers people try and come up with variants of graph isomorphism based on some fancy matrix, and they don't work. So my intuition is, I'm inclined to be fairly skeptical. But your question's a good one. I mean, it's not clear what you would you'd want to come up with an interesting class of graphs. But I suppose you could ask about planar graphs, for example. But,
thanks. Are there any other questions?
So was the perfect state transfer kind of inspired by an algorithmic point of view? Like you would actually have run the quantum walk from point vertex A and measure if it's in vertex B?
Well, it would be part of it would be a subroutine in a quantum computation. The issue is that, the state is in some sense being transferred from one qubit to another. Okay. Now it's more complicated for several reasons. One is that there's a time involved, so you can there's a time lag which you can't beat, and the other thing is that the underlying Hilbert space for the quantum walk is not really it's not n-dimensional. It's 2D n-dimensional, and so there's some other complications thrown in. But yeah, it would be at best a subroutine. Okay. Is my understanding.
And a small follow-up then is then in a quantum algorithm, it's really hard to distinguish between something that is some state B and state B with a little epsilon error.
Well, that's not the issue. The issue, as I said, this is equivalent to just trying to, if you've got a computer, you spend a lot of time transferring data from one part to another, and there's a thought that you might want to do that on a quantum computer. And then you have this problem, this so-called no cloning theorem that says you can't just do the obvious. There's no procedure which will take one state as input and produce two copies of it as output. Okay, and because your input state would be a density matrix D and the output state would be D tends to D, and that map is not linear. And lambda D goes to lambda squared D times D.
Okay.
You can make that proof a lot more complicated. But
okay.
Any more questions? Oh, sorry, I didn't see.
You be careful.
What's the point of studying discrete versus continuous quantum walks?
Sorry?
What's the point of studying discrete versus continuous quantum walks?
You can explain this to Harmy later on. Well, they're different models. The thing about discrete quantum walks is that you can represent, there's a natural way of presenting Grover's algorithm for search in terms of discrete walks. Okay. Also, some of the earlier stuff on quantum walks was looking at walks on the infinite path, and in that case, they were using discrete walks. The point is that these are all quantum things, and there's as a physicist once remarked to me, if you as a graph theorist come up with something mathematically interesting, then it's the physicist's job to implement it in a certain sense, if it's worthwhile. Okay, so the point is that you can view these things as part of a toolkit. Okay, now the discrete walks are harder to deal with than the continuous walks. Okay, and so, but you can, as I said, they've got their applications, and you can do things with the discrete walks, which I haven't mentioned. I mean, I was pretty focused on what I was doing.
Last question, if there is any. If there is none, we can take it offline. And I wanted to say that there is workshop going on due to the 75th anniversary of Professor Godsil, starting, I guess, effectively from today. Thanks for the graduate students of Greece for organizing it. And for now, there is a birthday cake just across the room. And thanks again for the great talk, and happy birthday.